Okay, so let's start. So in the last couple of classes, we discussed multiple access channels in some detail, and today we'll see from today onwards we'll see sort of the dual of the multiple access channel, which is the broadcast channel. Now, in a multiple access channel, we had multiple transmitters and one single receiver who has to decode the messages of all of those different transmitters. So one way to think of it is the sort of the uplink scenario in cellular communication, where multiple cell phones are trying to talk to a single base station. And the broadcast channel is basically the downlink scenario in cellular communication, where a single base station is trying to send messages or talk to multiple cell phones, right? So you have one transmitter and multiple receivers. In this example that I have over here, we have one transmitter and oh, this is the transmitter. So in cellular communication, you could think of this as the base station by a cell phone tower, and you have K receivers, which would be the users in a broadcast channel, right? And as we've always been doing in this particular course, we'll assume that the channel from the transmitter to the receivers is memoryless, and discrete and memoryless, but otherwise the the outputs are allowed to be correlated in some fashion. So this is the general setup of a broadcast channel, and as we did in the multiple access channel, our goal will be to sort of find out what is the maximum throughput that you can achieve for a single transmitter, or what throughputs are achievable when a single transmitter wants to talk to multiple receivers. All right, so that's going to be the agenda for the next few classes. We'll discuss broadcast channels in some detail. And then once I talk about discrete memoryless broadcast channels and also maybe Gaussian broadcast channels, we'll shift, we'll see some applications of MACs and broadcast channels and point-to-point channels to what I call fading channels. So we won't derive anything particularly new there when we talk about fading channels, but we'll see that the problem can be either simple or complicated depending on what kind of a fading model we consider. All right. So before I get down into broadcast channels, are there any questions from our topics discussion on multiple access channels? Okay, so the broadcast channel, as I said, has one transmitter and say K receiver. So this is a K user broadcast channel, and the channel will treat this as a black box. So given a particular symbol as input, or given a vector, if we send n symbols, if the transmitter sends n symbols into the broadcast channel, then each receiver gets n symbols at the output, y1n, y2n up to ykn. So the ith receiver sees yin, which is yi of 1, yi of 2 up to yi of n. This is what each receiver sees. The transmitter sends x of 1 up to x of n. And the relationship between the outputs given the input is described by the following joint PMF. So the probability that the receiver 1 sees y1n, receiver 2 sees y2n, and receiver k sees ykn, given that xn was sent as input to the channel, is basically given by this probability distribution. So for each I, so you have independence across the i's, but for each I, the y1 of I to yk of I are allowed to be correlated, and of course they depend on what the input to the channel is. Okay, so this is what we call the discrete memoryless broadcast channel, right, or DMBC. Okay, and so let's see some examples before we see the formal problem of communication over discrete memoryless broadcast channels. The following, of course, it's not with a discrete alphabet but a continuous alphabet, but probably the most common examples you will see in a digital communications or a wireless communication course. So this is the Gaussian broadcast channel, wherein each symbol is corrupted by independent Gaussian noise to each user. So at each time instant, note that time is slotted, we transmit across n time instants, and at each time instant, the sender is allowed to send a single real number x of I, right, and the receiver, each receiver gets a real number at each time instant. Yj of I is a real number, and each yj of I is obtained by corrupting x of I by independent Gaussian noise. So yj of I is equal to x of I plus zj of I, where zj of I we assume is IID Gaussian with zero mean and variance some sigma j square. So the noise variance to user j is sigma j square. So you have user 1 being x of I plus seeing x of I plus z1 of I, where z1 of I is Gaussian with zero mean and variance sigma 1 square, and so on. Right? And typically we impose some kind of a power constraint at the user. So we'll say that the two norm of xn should be less than or equal to n times p. So this is the power constrained Gaussian broadcast channel, k user Gaussian broadcast channel. Right? And we will analyze the rate region for at least for Gaussian broadcast channels, maybe the two user Gaussian broadcast channel. Okay, so this is a case. We started off with a case where the alphabet is continuous, not discrete. So let's see a couple of examples where we have discrete inputs and discrete outputs. So it's convenient to just think of binary inputs and binary outputs. So we'll also look at the so-called binary symmetric broadcast channel, where each x of I is corrupted independently so each x of I is passed through a BSC P to get the user's outputs. Right? So you have user 1 seeing y1 of I and user 2 seeing y2 of I. So y1 of I is obtained by passing x of I through a BSC with crossover probability P1, whereas user 2 gets the output of x of I when passed through an independent binary symmetric channel with crossover probability P2. So essentially, at each time instant, the transmitter is sending a bit. So x of I is either 0 or 1, and the bit is flipped with probability P1 to get y1, and the same bit is flipped independently with probability P2 to get y2. Right. So this is So in general, the binary symmetric broadcast, so any broadcast channel essentially requires three parameters. So the following sets of parameters to be described: the input alphabet, the output alphabets. So for k users, you may have k different output alphabets, and the channel has to be described by the probability mass function py1 y2 yk given x. Right, so all of these, so these put together completely specify uh, the discrete memoryless broadcast channel. Right, and in this case, in this particular example of the binary symmetric broadcast channel, uh, the input alphabet is binary. Each of the output alphabets is also binary. So yj is also 0, 1 for all j. And in the joint distribution, p y1, y2 given x of y2 given x, it turns out that y1 and y2 are conditionally independent given x. y1 given x 1 given x times py2 given x of y2 given x. And can someone tell me what this will be equal to? So for the
So
binary,
these be P1 and P2.
yes. So can you give a closed form expression for this, or how would you describe it? So of course, one way to just say is that okay. So for each uh, y1 and y2, so what are the possibilities? So y1 can be different from x, and y2 can be different from x. So y1 equal to y2 equal to x. So what is the probability of seeing a y1, y2 if y1 is equal to y2 is equal to x? So it's the
So 1
probability
minus
that,
P,
yes,
1
1
minus
minus,
P into P into 1 minus P, both.
it's 1 minus p1 into 1 minus
1 minus
p2
P.
because
Yes.
we're looking at
Yes.
different parameters p1 and p2. Okay, that's good. And now
Y.
what if y1 equal to x,
Y2
but
not equal to
y2
X.
is not equal to x?
So 1 minus P1 into P2.
Correct, 1 minus p1 into p2.
And then
Then the
Y1
other combination is y1 is not equal to x and
X. Y2 equal
y2
to.
is not equal to x, in which case it is p1 into 1 minus p2. And the last case is when y1 is equal to y2, but these are not equal to x. And that is p1, p2. Okay, good. So this is one description of the PMF of y1, y2 given x. Okay, that's good. Let's see another example. So let's take the example of a binary erasure broadcast channel, where basically I replace the two BSCs with two BECs. Right? So in this case, what is the input alphabet? It is binary, right? What are the output alphabets?
So 1, 0 and erasure.
Yeah, 1 0 and an erasure. So let me call it star. Let's say that star is my erasure symbol, and the okay, and now I also need to specify what is the PMF. So Py1 y2 given x of y1 y2 given x. So what is this equal to? So what are all possibilities that can happen?
So y1 equal to x1 and that.
Okay, so simple case is y1 equal to y2 equal to x. In which case, what is the probability of that happening?
That is 1 minus p into 1 minus p1 into 1 minus p2.
Correct. So it's 1 minus p1 into 1 minus p2. Okay, what is the other possibility that can happen?
So sir, in one case y1 equal to x and y2 not equal to
Okay, so y1 equal to x and
y.
y2, what can y2 be?
It may be not equal to x1 and it may equal to erasure.
But if it is not equal to x, then what is the probability of that happening?
So that is b.
You
Probably.
sure? So remember the BEC.
Okay, yes sir.
So a single BEC is the following, right?
Yes sir.
0, 1, and erasure. Right. So probability that you see a 1 given that a 0 was transmitted is always 0. And similarly, the probability that you see a 0 given that 1 was transmitted is also equal to 0. Right. So given that some bit was transmitted and the output, you either see that bit exactly or you see an erasure. Right. So it can so happen that y1 is equal to x, but y2 is equal to an erasure. Right? And what is the probability of that happening?
1 minus p1 and p2 into p2.
Correct. 1 minus p1 into p2. Similarly, y2 is an erasure, and y1 is equal to y2 is equal. So y1 is an erasure, and y2 is equal to x. That happens with probability p1 into 1 minus p2, and the other possibility is that both y1 and y2 are erasures, in which case the probability is p1, p2, and in the other case, I mean, anything else, the probability is 0. Right? So if y1 is some bit which is not equal to x, if it's neither x nor an erasure, then the probability of that happening is 0. Right? But these are examples, at least the three examples we've seen: the binary erasure broadcast channel, the binary symmetric broadcast channel, and the Gaussian broadcast channel is a case. All these three are examples where conditioned on x of I, the yj of i's are all independent. Right? So in this case, given x of I, y1 of I and y2 of I are independent of each other because they're passed through independent broadcast channels. Similarly here, y1 of I and y2 of I are independent given x of I because x of I is passed through independent erasure channels. Right? But it's possible that there could be a more complicated binary broadcast channels, and in general, all you need to do is just specify p of y1, y2 given x. So for example, if you had a binary input and binary output broadcast channel, you could have something like 0.1, 0.4, 0.2, 0.3, 0.9, 0.1, 0.05, 0.05, something like this, right? So as long as you specify a valid conditional distribution for y1, y2 given x, it's good enough, right? And in particular, it can be anything. All right. So these are examples of broadcast channels, simple broadcast channels. But then you can have more complicated channels where you have fading coefficients and so on. Right? But right now you could have fading coefficients, you could have multiple antennas at the transmitter and the receiver and so on. But we'll stick to simple examples. Okay, and we'll analyze these simple examples in some amount of detail. Right? So any questions so far? So the problem is, of course, now to design algorithms so that you can communicate reliably across such a broadcast channel. Okay, so think of it as though you have one person who's talking to two different people, and you have to talk to two of them simultaneously. Because one way to do so is to talk to person one and then talk to person two. But the question is, can you talk to both of them simultaneously in an intelligible manner? Right? And so formally speaking, the problem is as follows. You have a single transmitter and multiple receivers, k receivers, and the sender has k different messages for each of the k receivers. Right? So the first message is to be sent to the first receiver, the second message is to be sent to the second receiver, and so on. Right? So for example, if you think of if a typical cellular communication scenario, maybe the base station has to send some, maybe user one is watching YouTube, so you need to send the YouTube video to user one. User two may require, maybe he's talking over the phone, so you have to send voice data to the second user. User 3 is maybe browsing some website, so you have to send that data to user 3 and so on. Right? So you have independent, so the assumption that we will make is that these messages are independent, and the lengths of the messages could potentially be different, right? So you have L1 bits to be sent to user 1, L2 bits to be sent to user 2, and so on. So LK bits to be sent to user K. So MJ, LJ. So it's a sequence of, so the jth message is a sequence of LJ bits, and we'll assume that these are all IID and uniform. So it's just a sequence of uniform random bits. Okay, so that is the assumption on the message. And of course we are given this channel, so we can't play around with the channel anymore. So the goal is to design these encoders and decoders. So the encoder takes this sequence of messages and outputs a single code word. Right? So you can only use the channel n times. You can transmit only n symbols across the channel, and each of the receivers sees a sequence of n symbols, which are the received sequences. This is what we call the code word. And the goal is to ensure that the receiver, each receiver, can get its message reliably. So each decoder, so the decoder is going to be basically a function which takes as input the received sequence and outputs the desired message as output. So these are all estimates of the message. And the goal is to ensure that these estimates are good. So in the sense that the probability that the estimate is different from the actual message is vanishingly small as n tends to infinity. All right, so that is the sort of setup for a discrete memoryless broadcast channel. Now, sometimes people study this in a slightly different way. So here throughout we'll be assuming that all the messages are independent, and these independent messages need to be sent to each of the receivers. Right. So sometimes what people also analyze is the case where there is a common message. So in addition to these independent messages, sometimes these are called private messages. You could also, in addition to the private messages, you could also have a common message. Maybe let's call it M0, L0. Right? And each receiver has to not only decode its own private message, but also decode the common message. Okay, so each receiver has to decode its private message as well as the common message. But at least in this class, we'll ignore the common message part. It turns out that this can also be handled and you can analyze it, but it just makes things more complicated. So we will see. So we will study a simpler setup where you only have to communicate these private messages to each of the receivers. Okay. So of course, our goal is to understand at what rate. So what is the largest L1, L2 up to Lk that you can transmit? So you need to somehow ensure that you can transmit more number of bits in n channel uses, while still ensuring that you have good reliability at the receivers. So we'll say that a set of numbers R1, R2 up to Rk forms an achievable rate tuple, or we'll say that R1, R2 up to Rk are achievable over this discrete memoryless broadcast channel if it is possible to construct a sequence of codes. So it's a sequence of encoders and decoders, for one for each n, such that you have the number of bits transmitted is by the number of bits of private message for user I is n times Ri, and the probability of error, which is the probability that any one of the receivers makes a mistake in decoding, is vanishingly small. So the lim sup as n tends to infinity of the probability of any of the receivers or any of the decoders making an error is equal to 0. Okay, and our goal is to understand what set of rate tuples are achievable. Okay. And our discussion will primarily be focused on the two-user broadcast channel. Okay, so we did a similar thing for multiple access channels. We studied two-user multiple access channels in detail, and then I said that for k users, it turns out that for k users, it's a simple generalization. Okay, the capacity region for a k user multiple access channel looks very similar to that of the k user broadcast channel, of the two user multiple access channel, and essentially the techniques follow similarly. So we know exactly what is the capacity region of a general k user discrete memoryless multiple access channel. But unfortunately, when it comes to the k user broadcast channel, things become a lot more complicated. So there are many classes of channels for which we know what the capacity region of the two user broadcast channel is. But if you want to generalize it to maybe more than two users, 4 or 5 or more than that, then it's a completely unsolved problem. Even for very simple k user broadcast channels, we don't know what the capacity region is. Okay, and in fact, we'll see that for many two-user broadcast channels itself, we don't know what the capacity region is. So unlike the multiple access channel, where we had some way of evaluating the capacity region, for broadcast channels, the problems are still open. So if you find the capacity region of a general two-user broadcast channel, that will be a great result. All right. Okay. So this is the problem setup, and our goal is to understand what set of rate tuples are achievable. So the capacity region or achievable rate region or the capacity region is the set of all achievable rate pairs. K, in fact, it's not just the set, it is the closure of all R1 through Rk that are achievable. All right. So this is the quantity of interest. Right? So through, as we did for multiple access channels, we're only interested in sort of the first order rate pair. So we want to know what is the best Ri, so the best set of R1 through Rk which are achievable, and we'll try to at least answer that for some broadcast channels. So we'll have both an achievable rate region. So we'll have an inner bound on the achievable rate region by giving an achievability proof by showing that there exist encoders and decoders for which the probability of error can be driven down to 0. And then we'll also have an outer bound. We'll say that if it is not in a particular region, then certainly the probability of error cannot be driven down to 0. And we'll see that the inner and outer bounds don't always match. So the actual capacity region is somewhere in between, and we won't have a complete solution for arbitrary broadcast channels. Okay, so any questions? Okay, so let's start by looking at some simple bounds on the rate region, on the achievable rate region for a two-user broadcast channel. Okay, we'll just look at two users, one transmitter and two receivers, and we'll try to see what can be achieved and what is certainly impossible to achieve. We have R1 and R2. So as before, what is the simplest technique that you can think of? So I want some technique which you can implement, right? So what is the simplest approach if you had, what is the naive approach? So suppose that you were given a broadcast channel, and then you had to decide, or let's say that you have to talk to two different people at the same time. How would you talk to them? Would you talk to them simultaneously? Suppose that you want to tell something to one person and something else to another person.
Sir, with the time sharing approach.
Yeah, so basically time division multiple access,
Yes.
right? So TDMA. So you first communicate to one person, user one, whereas user two just doesn't hear. He doesn't care about what is being said. And then after you said what you wanted to say to user one, then you talk to user two and then send him the message, right? So for alpha, so you take some parameter alpha between 0 and 1, right? So for alpha n channel uses, you send the first message, right? You encode and send the first message to user one, and then for the remaining 1 minus alpha n channel uses, you send the second message, that which is intended for user two. Right? And when doing this, I mean, it's obvious that since you're using alpha n channel users to communicate to user one, you should be communicating at the maximum rate possible, right? So obviously you will communicate at the highest rate possible, and let's say that the highest rate possible is of course the maximum over all maximum of the mutual information. The maximum is taken over all possible px, the mutual information between x and y1, right? And it doesn't really matter what y2 hears, right? And for the second user, when you're using the remaining 1 minus alpha n channel users, you again try to operate at the maximum rate possible. You take the maximum of the mutual information between x and y2, right? So one point to note here is that since these channels could be different, the maximizing input distributions could also be very different, right? So the one which maximizes ixy1 could be different from the input distribution which maximizes I of x comma y2, right? So you take R1 to be equal to C1 and R2 C2. So essentially using TDMA, any point on the line joining C1 and C2 is achievable. Right, so this is TDMA. Right, so therefore any rate pair which lies in this entire region is achievable. Right, so this whole region is achievable. Okay, so this gives us one possible achievable scheme. Let us see what is not possible. Right. So here's a question for you. So let's say that okay. So is it possible to achieve any rate? So is it possible for user one to communicate at any rate above C1? Is it possible to communicate reliably at any rate above C1?
No, sir.
So similarly, for user 2, it's impossible to communicate at any rate above C2. Right? Because if they try to communicate, no matter what the other user, no matter whether the other user can receive reliably or not. Certainly that particular message cannot be received reliably, right? So certainly this region is not achievable. Right? So this is not achievable. Okay, great. So we definitely know that this is not possible. So any rate above C1, so R1 greater than C1, R1 greater than C1, or R2 greater than C2, not achievable. So any R1, R2 which satisfy either of these are not, certainly not achievable. Okay. So anything else? Can we do something else to? So now there's a bigger gap between these two regions. We don't know if any rate pair in this region is achievable or not. Can we get some other outer bound? Can we say that something else is not achievable? Right. So suppose that I consider a more powerful set of decoders. Suppose that the decoders could somehow cooperate with each other. Okay, so there was one single decoder which could see both y1 and y2 at the same time. Of course, it's not possible, but even in this scenario, if something is not achievable when the decoder can see both y1 and y2, then certainly by seeing only y1 or only y2, that particular rate pair is not achievable. So in some sense, let's assume that decoder 1 has access to both y1, y2. Decoder 2 also has access to both y1 and y2. So these are more powerful decoders, right? So in this case, what can you say about R1 plus R2? So if can you somehow use the converse for the standard channel coding theorem to say that some particular R1 plus R2 is not achievable? So if
Sir, I
you're
of y1, y2 and
huh,
mutual information between y1, y2 and xn.
so if it is greater than
Yes.
C12, which I define as the maximum overall possible Px of the mutual information between
Uh,
x and y1, y2.
yes.
Certainly, if the rate is above this, then that rate is not achievable, because this corresponds to the case when you have a single receiver which observes both y1 and y2 and tries to decode both of the messages together. So certainly, if the combined decoder cannot decode something reliably, then obviously if you separate the decoders, then it's impossible to decode reliably. Right? So certainly any rate pair which satisfies this is not achievable. Right? Uh, So this would maybe correspond to some particular pair over here. Certainly, this region is also not achievable. Okay, so that gives us another condition, right? So this corresponds to R1 plus R2 equal to C12. And certainly, so any rate which is outside these is not achievable. So of course, the natural question to ask is, so now we've narrowed down the set of rate pairs which are achievable and which are not achievable, but there's still a gap. So there's something in between over here, and we don't know if something is achievable in between or not. And that is what we will address in the next couple of classes. Okay. So any questions up to this point? So before we actually try to analyze a particular two-user broadcast channel, we will make some observations about general broadcast channels. So one key observation that we'll make is that the capacity region will actually not depend on the correlation between y1 and y2. So all that matters is just py given y1 given x and py2 given x. So how y1 and y2 are correlated among each other given a particular x does not really matter as long as we're only interested in evaluating the capacity region. Now, the correlation between y1 and y2 could help in designing a better decoder, designing a better encoder, and trying to get a slightly lower probability of error. But asymptotically, for large enough n, it turns out that this does not matter at all. Right? So for example, if you look at two different channels, so one channel is when you transmit X through independent BSCs, okay, and you get Y1 and Y2. Okay, so user 1 sees X pass through a BSC P, and Y2 sees X pass through an independent BSC P. So that is one particular broadcast channel, and this is different from the following broadcast channel where X is passed through a single BSCP and the output is shared between Y1 and Y2. So both Y1 and Y2 see the same thing. Okay, it turns out that both of these have the same capacity region. So in this case, Y1 is equal to Y2 with probability 1, whereas in this case, Y1 could be different from Y2 because Y1 is independent of Y2 given X. Right? Is there a question?
Yes. So said in previous slide.
Yes.
So is this bound means this is achievable and after that is not reachable? In between that line, red line and black line. So we need some marginal information like the joint the information of joint distribution information for achieving this blank region.
So you know, right? So you know what is P y1 y2 given X.
Yes.
Right. So the channel is given. But you need something. Obviously, you need a better technique than TDMA to get a better achievable rate, right?
Yes.
And you need a more powerful converse technique than just what we've used so far in order to say that something is not achievable. Right? So in general, the actual achievable rate will look something like this. It will be possibly some curved region, or it could be some other pentagon, depending on what the exact channel is. But in general, this region will be achievable, but so we'll need more powerful techniques to show that this particular rate pair is achievable, whereas anything outside is not achievable.
So we can use that approach, whatever we have learned similar to previous.
Correct. So we are going to use very similar techniques. We're going to use like random codes, random code books with joint typicality encoding and joint typicality decoding. Random code books at the input and joint typicality decoding at each of the receivers. But we'll see that the coding technique that we have to use for broadcast channels is slightly different. The ideas that we need for broadcast channels will turn out to be different from that of multiple access channels, and we'll see that difference in the next class or so. Even to get a better converse, we'll see that just Fanos inequality is not sufficient. That turns out to be that doesn't give you a good enough bound. You'll need some more powerful tools, and that is why we'll make use of some of the tools that we've already studied, Mrs. Gerber's lemma and the entropy power inequality and so on. Those will play a role when we derive more powerful converse bounds for broadcast channels.
Okay, sir.
All right. And one more thing is that it will turn out that the best converse, so for many channels of interest, the best converse bound will give us some particular region. So everything in the red region will be achievable. All right. And sort of these code books, we will see that it's called superposition coding, that will give us some achievable region. So everything below the blue curve will turn out to be achievable, but there will be some region in between where we still don't know whether this can be achieved or not. So there is, in fact, for many channels, for many broadcast channels, there is a gap between the best achievability and the best converse that we can prove, and that is why the problem is still open. All right, but we'll see some examples, some specific examples of what are called degraded broadcast channels, where we can say what the capacity region is. All right, any other questions? Okay, so I'll make this one last point and then we'll stop there. So it turns out that for any 2-user discrete memoryless broadcast channel, in fact, for any k-user discrete memoryless broadcast channel, the capacity region just depends on py given y1 given x, py2 given x, up to pyk given x. So the exact correlation between y1 and y2 doesn't really matter. So all of them have the same capacity region. So if we can find the capacity region for the case when y1, y2 up to yk are conditionally independent given x, then we can find the capacity region for any channel where y1 and y2 are possibly correlated. So note that this particular statement is valid when there is no common message. There are only private messages. So by that I mean that the sender wants to send independent messages to each of the k users. And really the reason why this is true is because the probability that m1 hat is not equal to m1 or m2 hat is not equal to m2, just by the union bound, this quantity is less than or equal to the probability that m1 hat is not equal to m1 plus the probability that m2 hat is not equal to m2. This is just by the union bound. The union bound. Right? Now this probability depends only on py1 given x. It does not depend on what is the relationship between y1 and y2 given x. This depends only on py1 given x. And similarly, this depends only on py2 given x. The exact correlation between y1 and y2 don't really matter. Right? So this gives an upper bound, but it is also lower bounded by the maximum of the probability that m1 hat is not equal to m1 and the probability that m2 hat is not equal to m2, where of course this depends only on py1 given x and this depends only on py2 given x. All right, and that is why ultimately the capacity region only depends on py1 given x and py2 given x. Right, so whether you're operating over this broadcast channel or over this broadcast channel, it doesn't really matter, right? But we'll see that even in the case where you have these independent channels, where it's a concatenation, where it's a series of independent channels to each users, we still don't have a complete solution. Even after making this reduction, we don't have a complete solution for arbitrary broadcast channels. So in the next class, we'll see a specific class of broadcast channels, and then we'll go on to derive both inner and outer bounds on the capacity region of these channels. Okay. Any questions? Okay, so in that case, let's stop at this point. We will continue our discussion tomorrow, where I'll talk about what are called degraded broadcast channels. We've already seen degradation in our initial early classes, and then we'll try to derive some. We'll see an achievability scheme for the two-user degraded broadcast channel. Okay. So all right. So let's stop at this point. So see you all in the next class.